Hey guys, hope you're all doing good and welcome to a new video. In the last video we finished the boundary flagging, and in this video we are going to be proceeding to the case setup. But before we do that, we are just going to fine-tune our boundary flagging a little bit so that it will be easy for us to apply boundary conditions. So I'm just going to set the model in top view and then view off of it. Oops, again I'm in vertex selection mode. Let me go back to triangle selection mode, use Ctrl H, and then I'll explain my thought process. So here what we want to do is you can see that this right here is your valve spindle, and this one right here you can think of it as your valve sleeve, right? So we want to be able to measure the loads on the valve spindle, and for that it would be great if that is flagged as a separate boundary. And the other thing that we want to do is we want to position the valve spindle at different locations. So hence we need to first figure out what is the current valve lift, and then we need to figure out how we are going to change the valve lift. So first let's just zoom in, and you can clearly see that there is a small gap between the valve spindle and the inlet portion of the valve. And if you look at the geometry is aligned along the z-axis, right? So the inlet axis is the z-axis. So if I zoom into the model and if I'm able to measure this particular gap, then I'll have my distance, right? But in order for you to measure the distance exactly, these two vertices should line up exactly. Currently they are not. So if you measure the distance directly, you might get something that is not exact. So let me make sure that I'm in the cursor pick option, select this one and this one, hit enter. You can see that the distance is 1.01984 e-3. That's about 1 millimeter. So that's not the exact distance. To measure the exact distance, what I'm going to do is I'm going to measure the location of this particular point, and I'm going to care only about the z-axis or the z coordinate, right? So notice that that is minus 4.18 e-2. That is nothing but minus 4.18 centimeters. I'll do the same thing for the lower point, and you can see that that's minus 4.28 e-2. So the difference between that is 0.1 centimeters, and 0.1 centimeters is nothing but 1 millimeter, right? Because 10 millimeters is 1 centimeter, so 1 millimeter has to be 0.1 centimeters. I hope that makes sense. If it doesn't, just work out the math. It's super easy. So currently the lift is 1 millimeter, and for our first steady state case we want the lift to be 3 millimeters. That means we want to move this valve spindle by another 2 millimeters. So first what I'm going to do is I'm going to go to boundary. I'm going to use the fence method, and I'm going to click on arc, and I'm going to select this guy right here, and I'm going to create a boundary fence. So now I should be able to go to flag, use the boundary fence method, and I should be able to select the entire spindle. And just by the preview you can see that we got the selection correctly. And let's just put it to boundary number 5. Okay, so now we have our valve spindle. So what I should be able to do is I should be able to go to transform, translate, selected boundary, boundary number 5 along the z-axis, and we want to push this by 2 mm, right? So that is 2 millimeters along the z-axis. So if I zoom in really close, click apply, you can see that the valve spindle got pushed up. And the nice thing is, if you look at the sleeve, it's made up of single triangles from top to bottom. So what would happen is it would just get compressed. So let me do undo here and pay attention to what happens in the sleeve area. You would have noticed that it just got elongated. So now let me just do the lift one more time. Correct? See that it's just getting compressed. If I do it one more time, the process is going to continue and we will not have any errors. So I have to undo this once so that I am at a lift of 3 millimeters. And always what you can do is you can come back here, you can measure the location of a vertex, hit enter again, right? And you can basically see that that's 3 millimeters. Right? You can basically subtract these two and convert that into millimeters, and if that checks out correctly, you should be good. Okay, so now that we have set up the spindle as a separate boundary, do we need anything else? Well, at this point, no. So we are ready to set up the case. So let's go to boundary and let's clear all the unwanted guys. And let us proceed to renaming all the components. So boundary 1, we are just going to call this as wall components, maybe wall at inlet. But if you're using this naming convention, then what you should do is for the top components you should have them as a separate boundary, right? But I'm not going to be paying attention to that. But however, when you are setting it up, I want you to make sure that you set up the names correctly. In this case, it really doesn't matter because all the wall components are going to get the same boundary condition, right? And this one, I'm just going to call it as wall casing. And I think boundary 3 is my outflow boundary. And boundary 4 is my inlet. And boundary 5 is my valve spindle. Okay, so I've set up all the boundary names. So let me go to case setup, begin case setup, general flow. Now in this particular case, what I'm going to do is for the steady state, I'm basically going to pretend that air is my fluid, and I'm just going to use that. So let me click on materials, use air, and click on apply, and click on yes, and click on done. And then global transport parameters, as long as your flow is laminar, don't worry about this parameters. So for now, let's just click on OK. So then we are going to proceed to the simulation parameters. So in this case, we are going to be using a density based solver, and we are going to be running it in full hydrodynamic mode directly because there is no moving parts. So let's click on OK. Let's click on yes for the subsequent options. And then for simulation time parameters, I'm going to start by running it for 15,000 cycles. Again, 15,000 is just a guess. Ideally, you will have to run it first and see what happens. Since we are using a dynamic time step, we can always start with a low value of time step. It should not be a problem if you have set up your simulation correctly. For max time step, I'm going to put in a value of 1 second. Solver parameters, nothing to worry here. So let's just click on OK. Now, before we move on to boundary conditions, I'm just going to create a region here with air as the working fluid and click on OK. So after I've done that, I'm just going to have my regions window open. I'm going to select my boundaries. I'm going to select all of my boundaries. Oops, not here. I'm going to go to view options. I'm going to select all of my boundaries, and I'm just going to add it to region 0. Let's click on OK. Go back to case setup. Go back to boundary. The regions have been assigned. So wall inlet, it has to be a wall boundary. Wall casing has to be a wall boundary. Outflow, I'm just going to call it as outflow, and I'm going to specify a pressure here. I'm going to put in a value 101325. Ideally, this has to come from some type of experimental data, and if there is backflow, I'm going to say that the species is air. At the inlet, what I'm going to do is I'm going to say that it's an inflow, and at the inlet I'm going to supply a pressure of 30 bar, right? So that's 3 bar and that's 30 bar. Okay, and air is going to be my fluid. Now this is going to drive a lot of velocity because the pressure difference is huge. So let me click on OK. Alright, so now you can see that there is an exclamation point here. Let's validate. You can see that valve spindle boundary is not defined. That's because that's just a wall type. So let me just set that. Click on OK. So you can see that there are no issues. For turbulence modeling, in this particular case, we are going with RNG K epsilon. For proportional valve applications or any valve applications, the most important thing would be the pressure force, and in general, pretty much all the turbulence models are going to do a decent job of getting you the pressure force. Unless you are interested in calculating the drag, don't worry about changing your turbulence model. So let's click on OK here. So now comes the base grid. So again, this is a totally different problem. So how do we approach the base grid? Well, you can do it based on your inlet. So what I can do here is I can measure the diameter of the inlet by clicking on measure, direction, arc normal, and I'm going to select 3 vertices on the circumference of my inflow boundary. Make sure that they are all on the same plane by rotating the geometry. Click apply, and you can see that that's 5.18 E minus 2, so that's 5 centimeters, correct? Now say that I want 10 cells across that gap. That would mean that I will have cells that are of the size 5 millimeters. Currently our base grid size is 4 millimeters, and I think that would be a great start. So let's just click on OK. So the next thing that I want to do is I want to go to output files, and I want to make sure that I'm generating wall boundary averaged output, and I would like to have 3D outputs written every 100 cycles, and I want to write text output every 1 cycle and restart maybe every 500, and I will be saving only 3 restart files. So let me click on OK for this as well and for this as well. So that basically concludes our case setup for the steady state problem. Now as part of your assignment, I want you to run this case setup for different valve lifts with and without adaptive mesh refinement. More details regarding this problem will be given in the challenge section. Alright, with that I would like to conclude this video, and I'll see you in the next one. Bye.